So this is an overview of COVID-19. And during this few minutes, I want to potentially answer some questions about what we know about the virus. How can we stop it? How does it cause disease? What are the prospects for a vaccine, which are obviously coming out, but what are prospects that will be successful? Can one be reinfected? How can one test for COVID-19? Do antibody tests work? Does the virus mutate? Are effective antivirals possible? And other questions. Now, this is a famous quote from Sir Francis Bacon, one of the founders of science, as it were. Scientia potentia est, knowledge is power. But of course, we don't have complete knowledge, so I would say that we should say some knowledge is power. And so hopefully, even though we can't share all of the details today, in fact, we don't know all the details, it's a continually evolving story. Hopefully with some knowledge will be better. So today's discussion will have several parts. We'll talk about the virus itself. We'll talk about epidemiology, how the virus attacks and causes mortality, how we fight back, how the virus spreads, namely transmission, what is to be done, and some other topics. So let's focus now on the virus itself. So what is a virus? A virus is a package of genetic material. It is contained within an organic particle that invades living cells and uses the host metabolic machinery to produce new virus particles. So notice that I didn't say that the virus is a living organism. In fact, the question is, are viruses alive? And that's a very important question when it comes to how we kill viruses, because if you cannot, if something is not alive, then technically you cannot kill it. So we'll address that important point shortly. So if we talk about the basic structure of the virus, it has three parts going from inside to outside. It has the nucleic acid, or the genetic material that we talked about, which in this case is RNA, ribonucleic acid, as distinct from DNA, and that has important implications. Second, it has a lipid membrane. Lipid is a kind of fat. And third, on the surface, it has proteins, most notably what's known as the spike protein. So those are the three major parts of the SARS-CoV-2 virus: the nucleic acid genetic material, the lipid membrane, and the protein. So let's look at these in a little bit more detail. The nucleic acid, as I mentioned, is RNA, not DNA. And RNA has a much more greater tendency to mutate than DNA. And this has important implications, as we'll see, for immunity and vaccines. And of course, this RNA is used for the testing in the PCR test. Second is the lipid envelope. It's a kind of grease that's around the virus, and this determines the environmental viability. So the virus is not like some hard metal, steel alien. It is actually quite fragile. And so soap and alcohol disrupt this membrane. Think about a soap bubble. Of course, it's an extremely nanoscopic, microscopic soap bubble, but it's not a hard particle. So soap and alcohol quite effectively disrupt this membrane. Now, the third element is that protein on the surface, and that determines the target. The spike protein, as we'll see, will target a specific kind of cell in the body, and that has important implications. Now, the other important thing about this surface protein is it's blocked by the antibodies. The antibodies are those molecules, defensive molecules, that are ultimately stimulated by a vaccine or natural immunity. And in some cases, the surface is also being used for testing in terms of the antigen and antibody tests. So we asked the question, are viruses alive? And you know the answer is no. So there are only two ways to get rid of the virus. One is to physically destroy it, for example, with the soap, the alcohol, and so forth. The second is to have it cleared by the immune system. There are no antibiotics for viruses, and certainly not for SARS-CoV-2 either. And this is what distinguishes, and perhaps may surprise people, is that bacterial diseases, we give the antibiotic and it's cured. And of course, we have the problem of antibiotic resistance. That's a whole another issue, potentially another pandemic, but let's not go down that road. But in terms of viruses, we don't have such a simple magic bullet. There's a lot of political issues around hydroxychloroquine and all this, and how we can, get rid of the virus with a magic drug. Uh, that was literally magical thinking. Now, that doesn't mean drugs are not useful and medicines are not useful in this condition, but they are not like antibiotics, which are for bacteria. So we'll get to this point later. Now let's shift to the basic epidemiology. Now, epidemiology is a very big field. So I'll focus on two dimensions of epidemiology. One is the mortality of fatality rate, which is on the vertical dimension, and the other one is on the transmissibility or how it spreads, which is on the horizontal dimension. So mortality and transmissibility. Now, generally, there is an inverse relationship between transmissibility and fatality. It's not a solid relationship, but there is a kind of relationship where if certain diseases, certain pathogens are less transmissible, they are more pathogenic, they're more fatal, such as bird flu, MERS, and Ebola. And those conditions that are much more transmissible, measles, for example, spreads faster, are generally less deadly. So more deadly up here, less deadly down here, spreads faster. So you have a kind of approximate relationship. The challenge of the new coronavirus, the SARS-CoV-2, is that it's in this middle space. It's not hugely transmissible, it's not hugely fatal, but it's kind of fairly fatal with certain percentages we'll discuss, and fairly transmissible. And of course, that transmissibility depends on social distancing and so forth. But if as a rough level, it's kind of in this middle space. That's one reason why it makes it so dangerous. It's not as scary as bird flu and Ebola that have 50% fatality rates. I mean, these are like bioweapons and whatnot and so forth. But it is just in this middle space, which from a population standpoint is in some ways almost worse because it's more transmissible. Spanish flu and seasonal flu are a little bit around here, but we're going to talk about what's the relation to that. So if we have these two dimensions of mortality, which I indicate in red, and transmissibility, we can compare flu and COVID-19. So for example, COVID-19 has a higher hospitalization rate and almost an order of magnitude greater fatality rate. Now, of course, that depends on age and conditions and so forth, but these are the overall population specifics. The other thing is it's more generally a little bit more transmissible than the flu with a R naught. We're going to talk about what that means in the 2 range, whereas flu is more in the 1 range. And the incubation time is longer, so that actually also increases this transmissibility. So now let's talk about how the virus attacks the biology of COVID-19. Some of this, of course, you are familiar with. So that means we're going to focus on this whole fatality rate, what relates to the mortality as we described. So the virus attacks what are called type 2 pneumocytes in the lung and a specific protein target in those cells, which is called ACE2 or angiotensin converting enzyme 2. And I'll talk about what these are more specifically. First, let's talk about the type 2 pneumocytes. So this is the lung, and the lung tissue, and if this white space is the air. So obviously lungs are for exchanging gases, carbon dioxide and oxygen from the outside to the inside. So there's a close connection between the blood in the lung, the capillaries, and the air pockets here. And the air pockets are surrounded by 2 types of cells, type 1 pneumocytes and type 2 pneumocytes. The type 1 pneumocytes or alveolar cells are relatively thin. They cover most of the surface, and they're involved in the gas exchange. The type 2 pneumocytes, which are the rounder ones, they cover about 5% of the surface. They're not a lot of cells in the lung, and they secrete a pulmonary surfactant. It's a kind of fatty substance that keeps the lungs able to breathe and open up, and the air can be there. Otherwise, they collapse from the surface tension of the water. So these type 2 pneumocytes are not actually the major part of the lung, but they're very, very critical for the lung function. If you are doing a military campaign, you have 2 options. You can either attack all the frontline troops, or you might take out the command and control center. In a lot of military strategy, it doesn't usually try to do an all-out attack on the most strongest and numerous elements of the enemy. A military strategy tries to aim for the command and control centers or to the vulnerable points. The type 2 pneumocyte is in effect the vulnerable point for the lungs. The flu actually infects more of these type 1 pneumocytes, so it has a more broader effect. It may seem more dangerous, but this type 2 pneumocyte is very critical, and you don't need that much virus necessary to start to compromise lung function. So SARS-CoV-2 infects these critical cells. So this causes lung and cardiovascular disease. So this is the lungs and the angiotensin converting enzyme 2. There's two types, angiotensin converting enzyme 1, which increases blood pressure, and angiotensin converting enzyme 2, which tends to decrease blood pressure and also decrease inflammation in the lung. Remember, we talked about inflammation in the mini-MD intro. So this ACE2 is on these type 2 pneumocytes, but also other cells throughout the body. And the SARS-CoV-2 spike protein binds to that target. That spike protein I told you is on the surface of the virus will bind to that, and that causes pathology or disease, and two types of pathology. Cellular pathology, it actually destroys those cells, as I said, makes it harder for the lung to breathe. So the destruction can be happen by the virus or by the immune inflammatory response. And also by reducing the ACE2 levels, remember ACE2 decreases blood pressure, you start to mess up the whole cardiovascular system. So on the cellular level, you have severe COVID-19 disease because you don't get the gases exchanging because the surfactant has been lost. On the molecular level, because ACE2 is involved in inflammation prevention as well, you get late stage inflammation and fibrosis, that inflammatory process. And then you also get the hemodynamic. Hemodynamic refers to the blood pressure and the blood heart rate and so forth. Because ACE2 is a critical factor in the blood pressure control, you get the hemodynamic abnormality. So even though you infect the lung, you start to affect the heart and the cardiovascular system, and it becomes a very dangerous situation. We call that severe COVID-19. Now, obviously, not all people infected get this. And the very open question is who gets that? And we know there are risk factors related to hypertension, cardiovascular disease, obesity, and respiratory disease that predispose to the development of severe COVID-19. But it's also beyond the lungs because there are ACE2 proteins in many other cells. So we talked about the lungs with the cardiovascular system, but you also have the intestines, the eyes, early cases in Wuhan, the brain, nose, loss of smell sense is very prominent, and also late stage disease in the liver and kidney. You have even been a talk of COVID toes in younger patients, and there have been clotting problems, probably related to the fact that the capillaries, not just in the lung, but systemically have ACE2, and it appears that COVID-19, or I should say SARS-CoV-2, infects those cells around the body that start to cause blood clots and arrange for the COVID, lead to the COVID toes. So symptoms of COVID-19, typically 2 to 14 days after the exposure, fever, cough, shortness of breath, sore throat, and very importantly, loss of smell. The flu tends to be a little bit more upper respiratory tract, so you might have sore throat and runny nose more with the flu, because obviously fever and cough are common to both, and then you may have more generalized symptoms with the flu, headaches, fatigue, body aches in early cases. Obviously, COVID-19, when it progresses systemically, has more of these generalized symptoms. So it's interesting, influenza affects those type 1 pneumocytes. Pneumocyte is lung cell, which are more numerous. So it kind of has a bigger hit on the body, but COVID-19 is more insidious and focuses on this kind of command and control or very vulnerable point. So it doesn't have such a big hit on the body, but it starts to affect critical body functions. So it's a very different biology. Even though obviously it's infecting the lung, it's a very different biology, mainly because of the difference between type 1 and type 2 pneumocytes. Notice the duality concept that we talked about with the logic of medicine. And allergies, of course, are more upper respiratory tract, sneezing, nose, eyes, itchy, red watering, and so forth. So there's all issues of hypoxia. We're not going to go into that with pulse oximetry and the oxygen levels. That's a little bit of a technicality. So I will move forward because I know we're getting late on time. So how do we fight back? Well, obviously, as I mentioned, we can either destroy the virus, cleaning surfaces and so forth. But of course, the way the body gets rid of it doesn't really kill the virus. It clears it by through the immune system. So the goal of the immune system is destroy or eliminate foreign invaders. Well, what is immunity? Well, there are two types of immunity, and some of you in the COVID-19 pandemic has really educated a lot of people who would not otherwise be exposed to this stuff. But there are two types of immune systems. There's the innate and the adaptive immune system. So that's that kind of duality that I mentioned. And the adaptive means that the innate means there's a general response to all pathogens. The adaptive response means there's a improved or changing immune responses to certain pathogens. So when the common lay term, I am immune to that virus, is meant to apply the adaptive immunity. So I become immune to that virus. But all of us have some sort of innate immunity to all of these viruses. It depends on how strong it is, from person to person and so forth. But when we talk about immunity in the non-professional sense, we're often referring to the adaptive sense. Now, this adaptive immunity can have two types: natural adaptive immunity or artificial adaptive immunity. And of course, if we get infected, we get natural adaptive immunity. Now, whether that lasts a long time or a short time is a question we'll talk about. When we get vaccinated, we call that active, call that active artificial adaptive immunity. Now, technically, the infected and the vaccinated immunities are the same, but the process, of course, is different. We can also have passive natural immunity, for example, the placenta and breast milk from the mother to the infant, pass antibodies. And then you've probably heard about convalescent serum or serotherapy, where antibodies are given to patients from previous patients who have been infected. So that would be passive artificial adaptive immunity. So the adaptive concept is that the immune system gets better at that particular pathogen, and we call that better response the secondary response, and that's a stronger response. So this is the antibody in response to the SARS-CoV-2 virus, and it basically blocks that spike protein from binding. And this is the initial response to that antigen. Antigen is what's on the virus, and that the antibody is what the body produces. So the initial response is like this, somewhat small. But if we have active artificial adaptive immunity or active natural adaptive immunity, then we will get a secondary response, those antibodies to A being much greater. And then if we have a new virus, then it will have this primary response, which is small. Presumably the secondary response will be greater. There are also other types of aspects of the immune system called cell-mediated immunity, which we cover in the mini medical school, that has an enhanced secondary response. So the key, apart from vaccine and all that, and of course social distancing, but the personal thing you can do is to boost as much as possible your immune system, to get enough sleep, to update your other vaccines, healthy eating to improve the gut microbiome, healthy fats, limit added sugar to decrease inflammation, moderate exercise, managing stress, and staying hydrated, and vitamin D and some vitamin C are all important. But probably the most important thing about boosting your immune system, and I'm very serious about this, is to get enough sleep. Of course, there's been vaccines in the news, all different kinds. Now we have 4 of them: Russian, Chinese, Pfizer, and Moderna, and so forth, the different types of viruses. I'm not going to go through all the different mechanisms and so forth, but I will say a few comments that are important. The good news is we have a lot of candidates or 4 passed the phase 3 clinical trials or near the end, as we mentioned. Uh, and because it's an RNA virus, we're not talking about something that's latent. Remember, I showed you earlier hepatitis. Hepatitis sticks in the body forever. Some of you may have heard of shingles, which is a herpes virus. It sticks in the body forever. HIV is there. These DNA viruses often get into the cells and incorporate the DNA into the cells, so it almost becomes a permanent situation. RNA viruses don't do that. So COVID-19, SARS-CoV-2 is probably not going to be one of these latent, long-term viruses that lurk in the body for the rest of your life. Uh, and also the good news is that it doesn't seem, at least in a very major way, to target the immune system. One problem with HIV, which we have never had a vaccine yet, by the way, as many of you know, HIV attacks the immune system. It attacks another vulnerable point, which makes it difficult to make the vaccine because the vaccine utilizes the immune system to create this enhanced secondary response. So we have good news. The bad news is that, like the common cold, the antibodies seem to be short term. You've heard of lifelong immunity and short term immunity. We don't know the answer yet because we've only had COVID for about a year, and certainly many places less than that, of course. So we don't know for sure, but there's evidence to suggest that the antibodies are not long term. And of course, there are other viruses like that. The influenza vaccine doesn't last for a long time, and some others need boosters and so forth. We may have a lack of neutralizing antibodies. The other problem is the fact that it's an RNA virus. In the mini medical school, we go over this in more detail in the biochemistry and all this. So it will be very clear as opposed to simply me telling you. But RNA viruses mutate, whereas DNA viruses are more stable. So that mutation means that the virus, the vaccine may have to change. Like the influenza vaccine changes every year because influenza is also an RNA virus. It also mutates. Other bad news is that the anti-vax sentiment and so forth, the social context could be a barrier. So why may antibodies not offer so much protection? Remember, the virus has 3 parts: the nucleic acid, the lipid membrane, the spike protein. It actually has a 4th part. The 4th part are these surface glycans, which are sugars, these little puffy portions on top of the protein. So the protein is under here, and these puffy sugars kind of shield the protein from the antibody recognition. So SARS-CoV-2, compared to the first SARS, has more of this uh, more of this sugars, and so that makes it much more harder for the immune system to latch on. So about 30% of patients fail to develop high titers of neutralizing antibodies. That was one study, but the vaccine studies showed 90% effectiveness. So I think the point is that these are not failures and so forth, but it's unlikely that we're going to reach those 100% levels, which would be good. What about antivirals? As I mentioned, unlike miracle antibiotics, which kill bacteria, antivirals cannot kill viruses. And there are all sorts of candidates, etc. We've talked about hydroxychloroquine and remdesivir and so on and so forth. But the point is the antivirals, they slow down the virus, allowing the immune system to clear it. They don't actually kill the virus. So anybody says, okay, you're going to be cured of something because of this antiviral, doesn't understand the fundamental biology. The antivirals can help, so I'm not making any political statements here. I'm just talking about the fundamental biology. You cannot kill something which is not alive. One thing about antivirals and medicines, a cautionary tale: the Spanish flu killed many millions of people. And some people believe that it might have actually been aspirin. Not the only culprit, of course, but aspirin had just come. It was like a miracle drug, and they were using huge doses, 25 pills a day, roughly twice the safe dosage. And that might have actually contributed to some, of the deaths. Not all of them, but I think it's quite clear statistics show, given what was happening, that it was not always benign, of course. So that's a cautionary tale. So how does the virus spread? So this is the green part of the graph. Sorry, I'm going a little fast. So we're going to focus on the R naught. Has an estimated R naught of 2.5 to 2 or so. Of course, that depends. That's the basic reproduction number. The actual effective reproduction number will change over time as the number of cases changes, as the social distancing changes, measures change, etc. So the R may decrease over time. What are the factors that decrease the R or determine the R? They're the intrinsic factors, the nature of the virus. So the virus has a certain transmissibility, it has a certain robustness, the lipid membrane, and so forth. It survives for a certain amount of period of time. These are the intrinsic factors, and that R may change with mutation. So the virus may get more transmissible, may get less transmissible. And then the extrinsic factors, which are related to two things: the nature of the population and the extrinsic factors relate to the nature of the population, which is related to the infection producing context and the mean infectious period, what we call the beta and the tau. I know that sounds a little complicated, but what I mean to say is social distancing and protective measures like masks affect this beta, how many people connected to how many other people and how closely are they. The tau is a time element, which is the mean infectious period. And one reason why COVID-19 is dangerous, it has a long infectious period. Flu is usually 2 or 3 days. Uh, SARS-CoV-2 can be about 10 days or so. So reducing that time is very critical. So we have different methods of transmission: direct, indirect, vector, and so forth. SARS-CoV-2 seems to be mostly direct, person to person, droplet, as well as fomites, as well as airborne. So there are many methods of transmission. One interesting concept, important concept, is that of lower versus upper respiratory tract disease. So upper respiratory tract is usually common cold. Lower respiratory tract, there's SARS and MERS. So upper respiratory tract, like the nose, the mouth, etc., have a high transmissibility and a low fatality. The very deep ones, like SARS and MERS, have a low transmissibility and a high fatality. But one of the dangers, as I said, of SARS-CoV-2, it appears to be both. It has both an upper respiratory tract and a lower respiratory tract component. So I will skip through this. We're running a little bit late. We have various primary mitigation factors for influencing those extrinsic factors. We have enforced lockdowns, unenforced lockdowns, voluntary social distancing, and minimal restrictions or herd immunity. The Korean experience, which is what I've been, has several points, 4 major points: intervening fast, that tau factor, test early often, contact tracing, and enlisting the public's help. And there are various factors involved in that. And they relate to that equation, beta and tau. So the beta are the social distancing methods, and the tau are related to the speed and the surveillance. So there are 3 ways to test for COVID-19. There are RNA tests, there are antigen tests, and these are diagnostic tests that you have the virus, and these are antibody tests that are called serological tests, which means you had the virus. And they also depend on the dynamic nature of the disease that we talked about earlier. So an RNA virus done too late might not pick it up. A antibody test done too early might not pick it up either. So finally, what is to be done? What should individuals do? Bear in mind that the great majority of cases are mild or even asymptomatic. Wear a mask. Cleaning and hygiene, social distancing are all very important. Ventilation, these are all not new. We saw this in the Spanish influenza. What should organizations do? Social distancing, minimizing contacts, managing contacts, flexible scheduling, smaller teams, cleaning areas, and so forth. Ventilation are very important. Of course, the mental health aspect, obviously you want team building, but not with personal touching, but still find ways to do a positive, supportive environment. So what do we know about the virus? It is very tricky. How can we stop it? Only by destroying it. How can it cause disease? Destroying type 2 pneumocytes. What are the prospects for a vaccine? It's possible, as we saw. Can one be reinfected? Likely false positive, possible immune failure. How does one test for COVID-19? Three ways: RNA, antigen, antibody. Do antibody tests work? Immunity may not be absolute, so likely not 100%. Does the virus mutate? Yes. Are antivirals possible? There's never been a curative antiviral particle. So that is it for today. I just wanted to end on this note. I want to thank you for your time. It's been a hopefully not too long, 2 hours. And I wanted to leave a few moments for Mac MC to make any comments about the upcoming January course. Thank you very much. And
All right.
you can reach me by email here as well if you have any questions.
All right. Thank you, Dr. Ogan, for that very insightful presentation. It's really a download for all of us. I mean, for some of us who are not in the medical field, yeah, it's very, very interesting. But anyways, for our attendees,